Okay, Assalamualaikum warahmatullahi wabarakatuh, and good day. Okay, today our class will continue on the second part of the chapter 4 magnetic circuit, which is the magnetic circuit. Okay, chapter 4 is magnetism. So in the previous class we learned about various theory. Okay, various theory on the magnetism. So you have to memorize the equation and the definition. Okay, and the application. So usually that question is half of your mark, okay, half of mark for chapter 4, and another half is the calculation of the magnetic circuit. So in the magnetic circuit, you will also have theory, but not too much. But usually the calculation is much more higher number of question. Okay, so I will introduce several parameter and then we can do the calculation. Okay, here I show you one example of a simple magnetic circuit. Okay, as you can see here, there is a core. Okay, core material and E is the voltage source. Okay, E is the voltage source. Okay, supplying the current to the winding. Okay, the winding of the core. Okay, the box is the winding and the box is the core and the winding is wrapped around the core. So basically, so you focus here. After the winding, in the core will produce a flux. Okay, flux symbol. Okay, you can see here. Okay, it move around the core, which has a length. Okay, L. Okay, length. So you can see here. Okay, that is the flux. Flux is basically like a current. Okay, in electrical circuit it's called current, but in magnetic circuit is called flux. But the characteristic is almost the same. Okay, and then you also have to know the area. Okay, okay, I will show you after this. So we have looked at the equation, so we will understand a little bit more about this. Okay, so basically, like, okay, I give you a simple example first. Okay, okay, assume the area is all same and the length is here. This is the length. Okay, this is the length. Okay, remember the effective length is at the center and area is the same. So basically area is the perpendicular to the length, okay, which is this part. Okay, so maybe I just use this one. So maybe the area is rectangular. Okay, so maybe this one is x, this one is y. So A is basically x, y. Okay, remember it is perpendicular. Okay, or maybe this one, L. Okay, remember x is goes into the screen or paper. And remember the winding. Okay, okay, this one is I. Okay, again this one is plus minus, this one is V. Okay, and this one is F. Okay, remember. So now you can know that the relationship is here is F equals to N I. Okay, this one is number of winding and okay, how many wind. Okay, if 10 winding. Okay, and the answer is in ampere. Okay, dot. Okay, so the unit is ampere dot turn. Okay, like I said before, ampere dot turn. Okay, also ampere also acceptable. And then the flux. Okay, flux. Okay, so remember flux is basically F divided by F divided by S. So what is S? Reluctant. Remember that I said you have to convert this into a okay, a circuit like an electrical circuit, okay, and then it has resistor, and then it has flux. Okay, this one is flux. Okay, this one is F. Okay, remember again, F it is at the winding. Okay, remember, not the voltage source, but it is a winding. Okay, winding. Okay, please don't forget. N-D-I-N-G. Okay, and reluctance is S. So how to calculate S? Okay, as you remember the slide before, S is basically F. S is basically F divided by flux. Okay, so basically this one. Okay, the relationship. But also S, there are two formula. This is the first formula. Okay, the second formula is the S equals to length divided by mu. Okay, mu A. Okay, so A is here. Okay, you can get the A and L. Okay, length and mu. Okay, and make sure mu. Okay, mu here is actually, okay, too large. Mu equals to mu not mu r. Okay, this one usually given. Okay, this one get from calculator. Okay, okay, basically remember mu naught is actually 4 pi multiplied by 10 negative 7, or you can use your calculator. And if you don't want to memorize 4 pi multiplied by 10 negative 7, you can use your calculator. Okay, so if you use your calculator, shift, use this calculator. Okay, shift 7. Okay, choose universal and then number 5. So the constant is saved in the calculator, or if you use the old calculators, I cannot show you, but it's basically at the back of your calculator. It shows how to get the constant. Okay, so make sure you either memorize this mu naught, or okay, you use your calculator. Make sure you know mu naught, and mu r is usually given, or sometimes you have to do some algebra manipulation to get mu r. Okay, depend on the question. So remember, S equals to L divided by mu over A. And remember also, okay, mu is actually also B over hash. Okay, if they give the B value and the hash value, you can get the mu. Okay, so permeability. Okay, make sure you know how to get mu and then how to get reluctant. And reluctant is actually mu naught mu r. Okay, make sure there are the equation. You have to memorize everything. So I mentioned in earlier, okay, for magnetic circuit, okay, there are calculation and there are some theory. So this is the theory. So you need to know the definition of each of these. So what is magnetomotive force? Okay, you need to know what is magnetomotive force. It is a driving force that causes the magnetic field to appear in the magnetic circuit. Okay, make sure you memorize this. Okay, so this one usually the definition will come out in the final. So make sure you know what is the magnetomotive force. And the formula is also important, because you want to do calculation, you need to know the formula. So F is basically equals to A and I. Okay, the unit is ampere. Okay, F equals to N is the number of turns of winding. Okay, how many one are turn, and I is the current supplied to the winding. Okay, so the unit is ampere. Actually, the unit is ampere turn. Okay, A dot, okay, A capital and then dot turn small capital. Okay, a small letter. Okay, so ampere turn. Okay, if you use ampere also, I accept it. Okay, so basically F equals to Ni. And then magnetic field intensity. Okay, also you need to know the abbreviation is hash magnetic field. Okay, magnetic field intensity and magnetic field, okay, is different thing. Okay, so make sure you differentiate this. Magnetic field is B. Okay, oh, magnetic field is, so B and hash is different. So magnetic field intensity is a mmf per unit length, okay, of the magnetic circuit, and it means vary from point to point in the circuit. So the unit also important, ampere turn. Okay, ampere per meter. Okay, ampere per meter or ampere turn per meter. Okay, and the calculation is just hash equals to F divided by L. Okay, magnetic field intensity. So remember the formula. So flux density. Okay, previously is hash magnetic field intensity. Then this one is flux density. So flux density is basically flux divided by A. Okay. So previously F equals to hash equal to F divided by I. Okay. For flux density or B, okay, is basically flux divided by A area. Okay. Make sure you know the flux is unit is Weber. Okay. Area of course B is Weber per meter square or Tesla. Okay. Make sure you know the unit. Okay. So what is flux density? It is measure of concentration of line of flux in a particular section of magnetic circuit. So make sure you memorize the definition. Again, reluctant, I mentioned before, reluctant is basically like a resistor in electrical circuit. Okay, so make sure you memorize what I highlighted here. Okay, the definition, it is the measure of opposite of magnetic circuit offered to the flux, basically like a resistant. So the abbreviation is S. Okay, resistor is R, reluctant is S. Okay, so the unit is ampere over Weber. So this one is basically S equals to, okay, F divided by flux. Remember that resistor R, Ni, okay, Ni is electromagnetic force, is basically like a voltage, and flux is like a current. Okay, so basically this is like a Ohm's law. Okay, so memorize this. Okay, another formula that is important in the magnetic circuit, okay, is the second formula. Okay, you can see S equals to L divided by B over hash divided by A. Okay, so make sure you know, memorize this. L divided by A, B over hash. B over hash is basically reluctant. I will show you B over hash is permeability. Okay, I will show you again after this. Okay, so make sure you memorize both of these formula. Okay, okay, this is the permeability I said before. Okay, so basically you have to know that mu, okay, mu equals to, okay, the U part is equals to mu naught mu R. Mu naught is the permeability in the free space, which is constant. You can check your calculator. Okay, it's basically constant. Okay, I don't remember the constant, but you can check it. Okay, usually it is represented as mu naught. Okay, mu R is the relative permeability. Okay, different. Okay, mu naught is constant. Okay, and mu R is different for every parameter. Every material. Okay, for air, you have to memorize this. For air, mu r is equals to 1. Okay, but for for other material maybe higher. Okay, like as example here, the nickel iron alloy is actually mu r is 100,000. Okay, and mu is basically the real value. Okay, the real value, the correct value of the permeability. Okay, so also mu also equals to b over hash. Okay, this one I said before. The ratio mu is equal to b over hash. Okay, it's called the magnetic permeability. Okay, for different value, okay, different material has different value. Okay, mu is basically the slope. Okay, the initial slope. Okay, I will show you after this. Okay, so okay, I show you what is the magnetic circuit. So there are various magnetic circuit actually. So I give you example here. Okay, the simple one. Okay, let me zoom out first. Okay, simple one is basically just a rectangular. Okay, you have the same dimension for each. Okay, you have the same dimension. Okay, then something like this. Okay, and then you have a winding here. Okay, and of course you have a voltage source, plus minus. You can call it V or you can call it V. Okay, remember I said it's either E or V. Okay, if you prefer V, you also can use V. Okay, because of the voltage source, it will produce current. Okay, so when it produce current, okay, what happen is, I said before, it will produce flux. Okay, it will produce flux. Something like this. Okay, this one is the direction of the flux. So remember right hand grip. Okay, so use that flux. Okay, flux is basically like okay, you use the right hand rule. Okay, you can determine the flux. Okay, so flux represent like this. Okay, and this one you have winding. Every time you have winding, it will be this. Okay, F. Okay, flux is okay, and F is electromotive. Okay, force. Oh, sorry. It's not electromotive force. Is magnetomotive force. Okay, remember the Lorentz law? Okay, that one is electromotive force, EMF. But this one is magnetomotive force. It is F. So be careful. Okay. So EMF is to generate. Okay, to generate electricity. But for F is to generate the magnetic field. Okay, magnetomotive force. Okay, so this one, okay, when it comes to magnetic circuit, it's harder for you to do this because you are usually do because in this course is mostly we do a electrical part. So basically what we have to do is convert this into something like a electrical circuit. Okay, what it mean by that is basically you change this into plus, minus, and then okay, something like this. Okay, okay, so this one is basically the flux. Okay, usually we use current, but now we change it to flux. Okay, and then this one, instead of using R, we call it S. Okay, S is reluctant. RELUCTANC, reluctance. and this one is not. Okay, this one is not this. Okay, but this one, okay, this one is actually the winding. Okay, make sure you differentiate when you use magnetic circuit. The voltage source here represent the winding and not the voltage source there. So basically this one is F. Okay, magnetomotive force. Okay, winding. Okay, so this is the basic. Okay, and then you also need to know length. Okay, L is the length. Okay, and A is the area. Length, effective length. Usually it's called effective length. Okay, what is effective length? What is length? Okay, basically when it comes to length, it's basically parallel to flux. Okay, so basically flux is parallel to length. If you want to measure the length, basically you have to look at the flux direction. Okay, so make sure effective lengths mean you have to take the center part. Okay, because the length at the outer side, okay, if you look here, the length here, okay, the length here is actually longer than the length inside. Okay, inside the core. So basically if you want to measure the length, make sure you take at the center. Okay, it is the effective length. And then how about area? So area, okay, area is actually perpendicular to flux, okay, or to length. Okay, because flux and length is the parallel, so basically area is the, okay, area is the perpendicular, means that, okay, so if you look here, the flux move like this, so basically the area is cross section here. Okay, if the flux move like this, the cross section here is the A. Okay, be careful, some area, okay, maybe this area and this area is not the same, so you have to measure correctly, okay, before you look. Okay, so basically that is it. Why you want to know the length and the area is basically you have to use it to calculate the S, okay, the reluctance. Okay, that is the basic. So remember that I said that for BH curve, okay, so BH curve, okay, the curve is usually like this. Okay, this one is saturated. Okay, so basically mu equals to B divided by H. So if they give graph, how to get mu is basically you look here. Okay, remember how to get the slope. So basically you get this point, okay, B, and then divide by this point, H. Okay, just do that. Okay, B divided by H, you get mu. Not mu naught or not mu r, but mu, the total permeability. Okay, the real value of the permeability. Okay, so basically this is the summary of what we have learned today. Okay, and the comparison between the magnetic circuit and electric circuit analog. Okay, and electrical circuit. So MMF or F, okay, magnetomotive force. Okay, the F1, F equal to Ni, is basically like a voltage source. Okay, flux is actually like a current. Reluctance S, okay. Beside S, you also can use R, but in this the like a very curly R. Okay, you can also use the curly R to represent reluctance, but usually we use S. Okay, and permeability also mu. Okay, if you compare to electrical, it is the resistivity. Okay, so this one we don't learn in electrical. Okay, also this one is the comparison. Okay, equation analog. Okay, Okay, Ni over flux is equals to 1L over mu A. Okay, the reluctant. How to calculate resistance, and it is compared to the resistor. Ohm's law, V divided by I equals to R. Okay, L over A divided by P is basically, we don't learn in electrical, so no need to worry. Okay, Kirchhoff current law, okay, also the same. Okay, flux, reluctant. Okay, this one also the same. Okay, actually you can use magnetic Kirchhoff current law and Kirchhoff voltage law in a magnetic circuit, but we will not go there because we only touch the surface for chapter 4. Okay, no need to worry too much. Okay, usually we only ask the simple question. So electrical circuit and its analog. Okay, so if you can see here, okay, magnetic circuit and its analog. So I mentioned before, you have to change the magnetic circuit into a electrical like circuit. It's basically called an electrical analog circuit. Okay, it's not electrical circuit, but it's represented as a electrical circuit. Why? Because it is easier to calculate. And if you can see here, okay, last example I show you only a simple core. But if the core is complex, you have to differentiate for each. Okay, remember that reluctance is L divided by mu A. So basically, if you look at this core, different section has different area and length. That's why there are many reluctance in this electrical circuit analog. Okay, so I will show you some example after this. Okay, in the earlier example, okay, I show you a simple core which has a same material and same dimension, and okay, so it is much more easy. But in reality, the dimension is not simple. Okay, so S, okay, or reluctant, S is equals to L divided by mu A. Okay, so if you can see here, there are two components. Okay, this one is dimension, okay, or the size, okay, and another one is the mu. This one is basically the material, R-I-A-L, okay, material. So basically, there are two things that affect the reluctance. Okay, so I give you a simple example first. Okay, for example, you have a core. Okay, then this one is a bit larger. This one is much more larger. Okay, larger. This one larger. Okay, and then this one is the largest. So basically, the winding is maybe here. Okay, so if you can see, the flux can flow like here. Okay, this means that this circuit is in series because the flux doesn't split to any other part. Okay, the flux only go in one path. So this is a series. So basically, remember effective length. Okay, so basically, okay, center, take the center. Okay, this one is L1. Okay, this one at the center to the center is L2. This one is L3, and this one is L4. Okay, so if you take the cross section again, okay, this one is area 1. Okay, because it is much smaller. This one is area 2. This one is area 3. This one is area 4. So remember the series, because this is a series circuit. It's same like a resistor in series. You just add it. So basically, total reluctance is just equals to, Okay, if you redraw this again, okay, I redraw this first. Okay, if you redraw this into electrical analog, okay, so basically you have a source, okay, minus, again this one is the winding, okay, F, okay, then you have a resistor here, okay, for A1, S1, okay, you for represent the L1 and S1. This one is S2, this one is S3, this one is S4, S4, S3. So because this is in series, basically, okay, S is just S total is just S1 plus S2 plus S3 plus S4. Okay, if it's in parallel, you have to use Kirchhoff current divider rule and everything. Okay, you can use all of this theory, but because this is in series, you just add it up. And remember the formula. So S total again equals to L1 divided by mu. Assume that this material, okay, same material. So mu equals to, okay, just mu, okay, it's the same mu. So mu A1 plus L2 over mu A2 plus L3 over mu L A3 plus L4 divided mu A4. So you can see here, okay. So basically you have to add everything with different dimension. How about different material? Okay. So if different material, for example, okay, I have a, okay, maybe this one. Okay, assume the dimension is the same. Okay. Okay, and then you have the winding. Okay, F, and then you have a material divide. Okay, so this one is material 1, this one is material 2. Okay, so basically assume that the A is same throughout the core. So basically A all the same, and the length, of course, this one. Okay, so assume that the length is L, okay, and L1, okay, L1 is material 1, L1 is equals to L2, basically L divided by 2. Okay, same length. Okay, so only the different material. So basically to calculate the S, of course, S total is equals to L1, okay, divided by A, but mu 1 plus L2 plus divided by mu 2A. So this one is basically the same, because it's the same, just L, don't forget, divide by 2, because it is 2. Okay, so L1 plus L1 plus L2 is equal to L. So that's why you have to divide by 2. So again, ST equals to L divided by 2. Okay, if you don't want to confuse, just use L1 plus L2 divided by A. Okay, if sometime, okay, so mu naught mu R, mu naught mu R. Okay, remember mu equals to mu naught mu R. Okay, R1 R2. Okay, remember mu naught is constant. Okay, doesn't change, but this one mu R1 and mu R2 is different, so you have to know the mu R. Okay, this one is mu R2. So different material, different value. Assume that they give a gap. Okay, they give a gap. Okay, so basically it will become, okay, previously they only like this. Okay, the analog is like this. So this one is S1, this one is S2. But if you get a gap means the air gap. You cut this. Okay, either you take it little bit, okay, give a gap little bit, or you cut it. Okay, so basically ST, okay, is equals to the same as here, L1 divided by mu naught mu R1 A plus L2 plus mu naught mu R2 A, and then plus, because you add a gap, okay, when you add a gap you get a S gap. Okay, S gap is basically L, okay, L gap, how much gap you give, then mu naught and A. Okay, why there is no mu R? Okay, you can put mu R, okay, mu R gap, but mu R, okay, remember that from the previous slide, mu R gap is basically 1. Okay, so A gap is basically 1. So basically you can remove this, just mu naught A. Okay, okay, there are two things you need to know. Okay, okay, this one, either you can, the question asks it is separated. If it is separated, means that you don't have to minus the gap. Okay, the material length is still the same. But if the question tells you that it is cut from one of the material, okay, make sure you minus L gap. Okay, make sure you minus L gap, because when you cut this, basically the effective length is reduced. Okay, so that is two parameter. Either you change the dimension or you change the length, or also you can change both. Okay, if it's changing both, you have to consider both. Okay, make sure you know how to change this to this. Okay, and then calculate this one. Okay, I suggest you draw the analog. Okay, so electrical analog. Okay, sometimes they given mark, sometimes they not, but I suggest you draw it. Okay, usually they give 3 out of 25 mark. Okay, and it is easier for you to see. So for this example, this is a parallel circuit. So basically when you transfer this, okay, you find the electrical analog. Okay, so basically you have the winding plus minus, okay, the F, okay, and automotive force, and then you have the resistor at the center here. Okay, okay, at the center here you need to consider also, because there are component here. So from here, okay, the length to here, okay, you have to, this is the cross section. So you have to consider that is a reactant in series. So as center, okay, and then 2, okay, assume that this area is the same. Okay, this area is the same, and the length start from here to here. Okay, so basically this one is S right, and then another one is S left. Okay, so from here to here, assume that the area is the same. And if the area is not the same, maybe this one is A1 area 1, this one is area 2, this one is area 3. So make sure you have 3, S left 1, S left 2, 1, S left 2, and then this one is S left 3. Okay, so you have to use the equation. Okay, and the parallel, parallel circuit is usually for electrical student. Okay, for you, usually not come out, but you have to prepare if the question asks. Okay, if this one is basically, for this case is S center plus S right, okay, parallel with, okay, S1 S left, F1 plus S left, 2 plus S left, 3. So basically you have to use the parallel law, basically S right, then S left, okay, the all of this, okay, S left, okay, divided by S right plus S left. So the same as resistance, okay, S center. So usually this one is not come out, okay, because it is too complicated and you need a lot of time to solve this. Okay, but if it's come out, you have to know how to do this. Okay, make sure you know. Okay, so this is the parallel if the magnetic circuit is parallel. Okay, same as in chapter 1 and chapter 2. First you have to find the total resistance, for this case total reluctance. Okay, so find S total. Okay, S total. So after you get S total, is you basically have this parameter. Okay, only one left because you have already simplified the reluctance S. Okay, this one is flux, this one is Fi. Okay, so basically from this you can calculate everything. Okay, so you already get as, okay, sometimes they give I, okay, F, sorry, this one is F. So F, remember F equals to Ni. Sometimes they give I, you get F, you get S, find Q. Okay, find flux. Okay, sometimes they give, for example, the question is give N and I. Okay, you already calculated S and then find you already give N and flux. Okay, they want you to find what is the current needed to get the flux. Okay, sometimes they don't give the mu. Okay, mu r. So based on this, okay, they give all, you have to find mu r. Okay, maybe the area. So basically you have to play around with this parameter. Okay, so another thing you have to know is B and hash. Okay, 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 B is just flux over A. Okay, flux over A, and hash equals to, okay, hash equals to, okay, okay, basically hash equal to F, okay, over L. Okay, so if you calculate what is the F, what is the B, basically you have to find the flux first and then divide by the area. Okay, the area is where you check the B. Okay, different area, different if the area is different for each place, make sure you use the flux and the area. For series, no need to worry because flux is only one, but for parallel, different flux. Okay, area, so you have to know where you want to check the B. Okay, check the area. Okay, so you have to use the area on which you want to check B. Okay, so then for hash, okay, of course the same thing. If you want to calculate this one is usually for simple circuit. Okay, hash, okay, use F, this one F, and then this L, okay, for the length. Okay, so you can find the magnetic flux. Okay, the magnetic field intensity for each length. Okay, so based on this, you have to memorize this also. Okay, So that is how you do a solve the magnetic circuit. Okay, we have concluded the chapter 4b, which is magnetic circuit. Okay, so for example, I will show you in the next class. Okay, for now you have to know what is the definition and equation of magnetic circuit. Okay, you have to know what is MMF. Okay, what is reluctant. Okay, the definition you need to memorize. Okay, what is MMF and reluctant and hash and B. Okay, permeability. So you have to know all of it. Okay, and then the electrical circuit analog. You need to know how to change from the magnetic circuit to electrical circuit analog. Okay, so make sure you know. Okay, if there is a different in area. Okay, different in area or length or the dimension and the material, make sure you represent it in the different reluctant. Okay, if the area is the same, the length is the same, just use the same reluctant. Okay, no need to the material also same, just use the same reluctant. Okay, make sure you know that. Okay, and lastly, the magnetic circuit calculation. You need to know how from the reluctant. You have to know how to get F, how to get N, I. Okay, based on this, you have to know what is the flux, what is the relationship, and don't forget the B hash. Okay, how to get B and how to get hash. Okay, that's it. Okay, see you again in the next class.